ladies and gentlemen, to this video lecture. Okay, so we are busy discussing improper integrals, and now there is a second type of improper integral that we need to discuss. Okay, so this type of integral, improper integral, or let me first discuss the improper integrals that we have already discussed. So if we have already discussed improper integrals over unbounded domains. So for example, if you want to integrate up to and include or up to infinity. Now there's a different type of improper integral which we call an improper integral of type 2. So for example, if a function has a singularity, so for example, if close to some point we divide by numbers that get larger and larger and larger, and the function is not defined at that point, we might still want to be able to compute the integral of that function. And this is what we will now discuss. So, definition. Let f be a function from a to b on the half-open interval. Let f be continuous. And now I'm going to explicitly say here, note that f need not be defined. At b. So note that f does not need to be defined at b. Now by the following, so by, and I'm going to put this in quotation marks, by the integral from a to b of fx dx, we mean the limit as t tends to b from the left of the integral from a to t of f of x dx. And if this limit exists, we say that our integral is convergent. Otherwise, we say it is divergent. So if this limit exists, we say that the integral from a to b of fx dx is convergent. And otherwise, we say that it is divergent. Okay, so in this situation, what do we have? Perhaps we have a function that is defined on the open interval from a to b, but here at b our function blows up or has a singularity and is not defined at b. So this is the situation that we find ourselves in. Okay, and there is a similar definition for when our function is not defined on the left endpoint of the interval on which it is defined. So let's call this number 1. So this is number 1. Number 2, if we have some function g from a to b, continuous, then by the following, and I'm going to put it in quotation marks, by the integral from a to b of gx dx, we mean the limit as t tends to a from the right of the integral from t to b of gx dx. And again, with the same definition of the words convergent and divergent. So this integral is convergent if this limit exists, otherwise we say our integral is divergent. Okay, and now there's a third case. If we have some function h which is defined on the interval ab, and then from b to c to r. So notice here this function is not necessarily defined at b. Again, by the following, the integral, and I'm going to put it in quotation marks, the integral from a to c of hx dx. We mean, of course, now there is possibly a singularity here at b. We mean, or let me write it this way. Let me write it this way. We say that this integral converges if both the integrals from a to b of hx dx and the integral from b to c of hx dx converge. And notice here we have these endpoints at b where the function is not defined, so these two integrals are defined in this way as limits, as we did previously. And otherwise we say that the integral from a to c of hx dx is divergent. And let me reiterate here, both of these must converge. And let me just make an illustration of what such a situation would be. So you've got an interval from a to c. However, at b, our function has a singularity or blows up. So for example, you've got a function that looks like this, and here close to b it blows up, and on the other side as well. And now we may still want to be able to compute the integral of this function. So what do? We split up this function down b, and we treat each one of these intervals separately. And if you look at the definition of how we define these integrals, we take for the right one, we take a t, which we then take the limit as t tends to b, and we look at this integral as t tends to b. So as t gets closer and closer to b, our integral gets closer and closer to the actual value that we are looking for. Okay. So in the next one, we will look at an example. I will see you in the next one.